Well, hey there, and so welcome to the final. It's just a mini lecture, don't worry. And I wanted to end just end with some application that I could talk off or something to do with quantum information, just like a introductory thing. I understand that it's a bit late, much later than what I was expecting. So I'm doing this as an extra credit assignment. You are invited to view the video and answer a couple simple questions. And if you don't have the time to do it for any reason, then it's an extra credit assignment, meaning it helps your grade if you do it, but it does not hurt your grade. And I can make that thing a little more explicit when in an email. Um, I'm calling the title of this mini lecture Quantum Magic. So I'm hoping to incentivize you to come take a look. And I wanted to show you something that is made possible by quantum entanglement. I wanted to show you how quantum information works and show you that there are aspects of quantum information that are actually enabled by quantum uh, entanglement, and they would otherwise be impossible if the information was not entangled. Okay, so yeah, I mean, let's get started. I'm kind of excited to talk to you about it, and let us begin. Okay, so you see, this says mini lecture, like as promised, and what it's about is quantum information. And so we'll talk about quantum entanglement. Okay, and what it enables. Okay, so the first thing I'll talk about, and these are all just very brief introductions, that what is quantum information? Okay, and so let's call this actually topic one. Okay, then topic two would be what is the basic, um, let's see, how do I want to do this? So then topic two would be, I guess, what is entanglement? Okay, so simple working rule definitions. And then three would be what's the basic setup for quantum communications, where quantum information is sent back and forth. And so this sets up the Alice and Bob sort of situation, which some of you may have heard of. And four is, I call it quantum magic. Okay. And so this is, in other words, enabling the impossible. Okay. And really, what I mean when I talk about quantum magic is, the idea that we have some very sane, decent logic, okay, that I'm going to call it the logic of, the sane, decent logic of local realism. I mean, and it's like any person would argue things based on this. And what happens is that this conflicts with quantum mechanics. And so experimentation is the only way to resolve which one is correct, because they both, uh, give very concrete predictions that are contradicting each other. And so it drills deeper into the idea of the EPR paradox that we have talked about earlier. Okay, so let's start, and hopefully you will have a bit of a fun time with this. Okay, I think it's a nice way to end what to talk about in the last lecture or two, and so this seems like an interesting topic to me. Okay, I need some more paper. So let us first start with what is quantum information. Okay, and so you know first of all, classical information, and let me set the dates here. So it's the 12, and it's supposed to be, the lecture was supposed to be on when? Today is the 7th, so Friday 6th, Thursday 5th. So let me just do that. Okay, and this is slide 2. So classical information, that we use bits, 0 or 1, right? And then what about quantum information, qubits? These are the states 0 and 1, okay? And then, of course, and any superposition state, which we talk about as some kind of superposition of 0 and 1, right? And of course, this is the two-state quantum system that we have analyzed in some detail, right? There's two possible states. You can have a superposition. Um, and so 0 and 1 are referred to as the computational basis. In quantum information, in the field of quantum information, these are referred to as the computational basis. Okay. So now the nice thing, of course, is that they're just a two-state quantum system. And so I think of these, can think of these as your good old friend, this the spin half particle, as spin half particles, which we actually have expertise in, right? So, because, and how do we know we have expertise? Because we have the whole formalism developed for dealing with spin half particles. For starters, let's just write these out. The four Pauli spin operators apply. And what do they do? I mean, so if you recall, I mean, you can look at please look at the lecture notes from 11/21/24, slide 2. Okay. And so I can, just to remind you, sigma z, well, the four polyspin, yeah, sigma z acting on 0. Now uh, let's be concrete about one thing here. This state 0, we can define it as 1, 0. Okay, and this guy, state 1, we define it as 0, 1, right? So we can, and these are things we've done before. So now the z operator acting on 0, you know will give you uh, just 0 with eigenvalue plus 1, right? Eigenvalue plus 1, state 0. And then, of course, sigma z acting on the other state, 1, it gives you back 1, but with eigenvalue minus 1, right? So there you go, all right? Um, Sigma x on 0, it flips the bit, gives you 1, okay? And sigma x acting on state 1, it flips the bit to 0. All right, I can, well, let me write out the relations and then I'll prove them to you. Okay, I'll show you one and you'll be required to show the other. Okay, so this gives you I1 and sigma y on the other uh, state gives you a minus I, 0. So the flipping happens, but there's with an I and minus I. And then the last one is the identity operator, which of course gives you back the original states. Now, just to prove this, and remember, you can look in here. Just to prove this, let me do this one for you, right? So you remember, if you look at those lecture notes, then you'll see that sigma x is 0, 1, 1, 0, right? So therefore, uh, sigma x acting on 0 is 0, 1, 1, 0, acting on 0, which is this column vector, right? And you can see from here, if you carry it out, right? So this is your 0 vector, and you get 0, 1, which is that vector, right? Now, so here's your first assignment, and there will be 2 questions, okay? So it's like a remote assignment instead of the in-class assignment, right? That you can verify for sigma y and sigma z that these 2 equations are uh, correct. Okay, so sigma y and sigma z. Okay, so that the above, how many equations are there? 1, 2, 3, 4. 4 equations are correct. Okay, and so this is remote assignment 1. There will be one other, similarly simple. Okay, and you can send it, just take a picture of your work and send it to me. All right, so you can check these all out. And so we'll use these relations in the subsequent slides. And just to end this, let me also say that you do recall further, recall from previous work what the eigenstate of sigma x is. Okay, further recall that the eigenstates uh, for sigma x. Okay, sigma x. If you can check, we worked all these out either in homeworks or in class assignments. That and you can see that, you know, if sigma x is flipping the bit, flips 0 to give you 1, flips 1 to give you 0, then the eigenstate is clearly, you know, you can form sums and differences of these, and those sums and differences would be eigenstates for sigma x. So you can check for yourself that the eigenstates for sigma x are 1 over root 2, just to get the normalization right, and you have a 0 and plus or minus 1, right? And so what I'm going to do is um, I'm going to call 1 over root 2 the plus eigenstate. I'm going to call it 0 prime, okay? And the other one, and 1 over root 2 0 minus 1, I'm going to call it 1 prime, okay? So we'll use this. Okay, I think this is all I wanted to say. So these are eigenstates, meaning if I uh, take sigma x and act with it on 0 prime, I will get the state back, 0 prime. And if I take sigma x and act on 1 prime, then this minus sign, you'll see when you act and the bits get flipped. So you have a 1 prime and with a minus sign. Okay, so I got these relations here. So actually, yeah, I mean, I should have been numbering, I guess, things as I go. Um, should I do that? Okay, let's just do that. So then this would be 1. These would be 2. Um, and right here, all of these would be equation 3. Okay. So we've done these things before. Shouldn't be a surprise. And please notice that here's your first remote assignment, a very simple assignment. You just have to verify uh, the top equation and the sigma y equation. Okay, and all the operators sigma y are provided in the lecture notes, and the definitions for 0 and 1 are given right here and elsewhere in our lecture notes. Okay, so okay, cool. So this is what we think of when we're talking about classical information versus quantum information. Okay, and now of course it's a matter of what was our next thing. So what is quantum information? Well, it's defined in terms of these two these like spin half like particles, which are the qubits. And now I'm going to talk about what is entanglement. Okay, so let's go to the next um, page and talk about what is entanglement. Now that I have the qubit language down, let's talk about entanglement. So this would be 1205 24 3. Okay, and so entanglement. And let's, because I'd numbered these, so 2 entanglement, and this is 1 classical information versus quantum information. Okay, so these are your classical bits, but then you have your qubits. Okay, entanglement. How do we talk about entanglement? So, what is entanglement? Well, so let's start there. What is entanglement? Well, a state, let's start by what is not entangled. A state that is not entangled is a state of 2 or more quantum systems um, so it's not entangled if this state of 2 or more quantum systems um, can be factored into a product of single system states. Okay, so if they can be factored, if these two or more quantum systems can be factored into a product of single system states, then these um, these quantum systems, I mean, this the final state of these multi-quantum systems, it is not an entangled state. So if factoring can occur, then it's not entangled. Okay, so 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 that completes that sentence. All right. So two or more quantum systems, if you can factor the final state into a product of single system states, then uh, that state that you're talking about that describes all these quantum systems together, it is not an entangled state. So what that means is that states that for which this cannot be done, so states that do not have this property, which property? This property of being able to be factored, okay, that do not have this property are entangled, are considered entangled states. Okay. So if you have a state of two or more quantum systems that cannot be factored into a product of single system states, that state is an entangled state. All right. So that's how these are defined. So if I want to write it mathematically, so let's just take two quantum systems. For two quantum systems, A and B, the combined state, okay, let's call it psi AB. So, that is, so I'm expressing the same idea, but now in sort of math language, I guess. The combined state psi AB is entangled if psi AB cannot be written as a simple product of the two vector spaces for A and B. Okay? So what it's saying is that the two vector spaces uh, cannot be neatly separated out from each other. All right. And so let's call this now, what was the last equation that we have? Equation 3. So let's call this equation 4. Yeah, so just bear with me as I set up the context, and then I will show you some quantum magic at the end. All right. And it's really mind-boggling. So let's continue with this. So, okay, so there you go. And so now, okay, so this is all the stuff that cannot be done, but how do I, like, what do I work with? So here's a entangled state now. So consider now here was a single qubit. That's a single qubit, but now I need two or more quantum systems, right? So I want two quantum systems. So I'm going to have a two qubit state. So consider the two qubit state. Okay, so, or in other words, a pair of qubits. Okay, and so here it is. Psi is equal to, and what it is, it's going to be a 0 and a 1. Now you've seen states like this when we were discussing EPR paradox. If you go back, look at the lecture slides for the EPR paradox. Uh, so this two qubit state has two qubits. So I mean the first one could be 0 and then the second one could be 1, or the first one could be 1 and the second one could be 0. right? Something like that. And let's now write a superposition of these two states. So your two qubit state is a superposition of these two possible states, and it's a superposition. So let's just go with this. So, and you could also have a plus in there, but I mean, let's just consider this for concreteness. All right, so this is equation 5. And what you can see from this is that, this state is not entangled. So that's how we're going to think of a pair of qubits. And you notice that these pair of qubits, they do not form an entangled state whenever theta is some multiple of pi over 2, right? Because I mean, if theta equals an odd multiple, then you notice that psi becomes odd multiple of pi over 2, which means the cosine goes away and you're just left with a minus. The sign is 1, so you're left with a where you notice that the two vector spaces are factored out neatly, right? So that's why this state is not entangled, okay? When this happens, and of course, if theta equals an even multiple of pi over 2, then psi equals, and this time the sign goes away, right? And you're left with the first one. So then it's 0, 1, right? So, so note that this state equation, the equation 5, psi in equation 5, okay? This state is not entangled for this, but otherwise it is, right? So, but um, for all other values of theta, psi is entangled, is an entangled state. Okay, so now I think we are at the place where we can start setting the stage for the quantum magic, right? So what I'm going to talk about now is this entanglement uh, allows us this entanglement allows us to perform a number of tasks which without entanglement would be impossible. Now, if you were doing a course in quantum information, then you will find that there are also a number of tasks which without entanglement are just less efficient. And so the speed of, for example, computation and when we're talking increasing efficiency, we're not just talking factor 2, factor 10, factor 100. It's more like million. So which without entanglement would be impossible. Okay, so I'll show you one example today. Okay. So I guess to get to that example, the next thing to do is to just set up the sort of basic architecture for how, so let me see, what was the number 3 thing? So we've discussed what's quantum information, that's just the qubit, and then and the fact that it's a spin half system, so you can use poly spin operators for manipulating the qubit. And then, what is entanglement? We just discussed that. Now, I just want to set up to discuss this quantum magic stuff. I want to set up the basic situation for quantum communications. All right. And so let's look at that. So this would be slide 4. Okay. So this is point 3 now. And so it's just the quantum communications protocol, or just the how things are set up. So, here we talk about, and this is just very simple stuff, I mean, that I'm discussing right now. So there's always, actually, there's always information um, source. Okay, and then there's a transmitter. Okay, and then from here, there's a signal. Okay, and so the information source, of course, uh, produces the choice of image, choice of message, I mean, to be sent. Okay. And then, so then now there is a sort of something happens here where actually, you can have a noise source which sort of adds to the signal as the signal is being sent to the receiver, right? There, so now this is going to be received in the receiver. Received signal, the receiver, and then finally, this makes its way to this destination or the detector. Okay, and so this receiver receives the noisy signal. I mean, if nothing else, then just atmospheric disturbance if the signal is going through free atmosphere. Okay, so it receives the noisy signal and the receiver converts it to a message. Okay, so there was a message that was sent, there's some noise that occurred, and the message gets sort of distorted because of that. Okay, and finally, I guess the thing is that, we refer to the person who is doing the choosing of the message to be sent and transmitting, and all this is all we, A for Alice. Okay, and the person who does the receiving, trying to interpret the signal, the message that was sent to him, we call him Bob. Good. So Alice wishes to send a message to Bob, and so Alice is, we're talking about a two quantum system in this case. So Alice's uh, event A is, the selection, um, of a message, from several possible messages. She selects one and transmits it. And Bob's event, that's kind of implicit. And Bob's event B is the detection, you know, of the message from Alice. Okay, so that's kind of the protocol and the situation that we're talking about. Okay, so now we're down to the final topic, which is um, what happens when Alice uh, tries to um, send information to Bob where she tries to send entangled information. How to talk about sending entangled information, and what are things that what are the unexpected odd things that happen when you try to transmit and detect an entangled state. Okay, so let's set that up now. So number 4 slide. So this is where the quantum magic will occur, all right? So because what we're going to see is that if Alice and Bob are trying to communicate entangled states, or if they are in possession of an entangled state and then try to communicate, okay, then they can do things which are sort of unexpected, unimaginable. All right. So let's try and analyze a situation like that. And so here's the finally, as promised, quantum magic. Okay. And so what we're going to do is we're going to consider. So please, so this is if there is one place where, like they say in the airplanes, that put up your tray tables and put the seat belts on and take a, sit back and all that. So here's where you need to pay attention now. All right. So let's consider a pair of qubits as we defined on a previous slide. And also, what's the title here? 120524, slide 5. Okay. Consider a pair of qubits. And of course, these pair of qubits, meaning a pair of spin half particles, because a qubit is just a spin half system. Okay. Consider a pair of qubits, uh, one held by Alice and the other by Bob. Okay. But they are prepared in an entangled state. Okay. So prepared. So one, Alice holds a qubit, Bob holds a qubit, but the qubits are entangled with each other. So prepared in the entangled state. Okay, here's the entangled state. Um, I'm going to give it a special name, so just one moment, but here's the entangled state. And it looks a little sort of strange, but not that strange. So you have Alice's qubit in state 0, Bob's in B, state B, in state 0, I mean, Bob's qubit in state B. But then there are other possibilities that Alice's qubit is in state 1 and Bob's is in state 0. And then the third possibility, Alice's is in state 0, Bob's is in state 1. Note that I've not put in the possibility where both of them are in state 1. Okay. Now, the choice of this state really brings home something which, I mean, you tell me where I made the error. It almost seems like there's no error really in calculating the probability, a certain probability, which you will see. based on just honest, decent, sane logic, it's very hard to see what the error is. And quantum mechanics, of course, has a completely different prediction. All right, so it's very much like the EPR paradox, but maybe things weren't quite clear in the EPR paradox as we discussed polarizations and linear polarizers versus circularly polarized light. Here, it's just going to completely bring it out in the open. All right, and the credit for this goes to a gentleman called Lucien Hardy. Okay, so that's why I'm calling this the Hardy state. Okay, and Lucien Hardy published two PRLs. Okay, so here's why it took a little time, guys. I mean, I needed to sort of find this, and I mean, it has been discussed in the literature, and it's a beautiful. There were two PhysRev letters published by Lucien Hardy, PRL. Now, don't worry, you will not have to go and read them. But I'm just giving this reference because, who knows? There might be someone who might feel motivated to go take a look, especially the theorists in the class, theorist inclined people. So PRL in 92, and then another one in 93. So here are the references. And they kind of took the physics community by storm at the time. Um, Quantum information was not quite on the everyone's horizon at that time, but it was taken notice of. Okay, so he proposed, let's consider that Alice and Bob share an entangled state like this one, right? And Alice has her qubit, which is labeled by A, and Bob has his qubit labeled by B, and these are the possible manifestations of this entangled state. And let's also see what formula number we're at. So this was 5. Let's call these as 6, which then puts me at equation 7 here. Okay. Now, what Hardy said is that notice, so Hardy said that uh, we can express equation 7, the state 7, equally well. Now, these are eigenstates of sigma z, right? But equally well in terms of eigenstates of sigma x also. Okay, now what was the eigenstate of sigma x? You recall that, here, the eigenstates of sigma x, 0 prime, 1 prime, right? And let me write it out in terms of that. So what I'm going to say is that, okay, so let's write it out. So Hardy can be, so I can write the same state in equation 7 also as square root 2 over 3, 0 prime A, 0 B, right? Plus 1 over root 3, 0 A, and Bob's state in 1, qubit in state 1, all right? And so this is equally the same, right? And I'll prove that to you in just a moment. And you can also write it as 1 by 3, 1, Alice's qubit in state 1, Bob's qubit in state B, plus square root 2 over 3, Alice's qubit in state 0, Bob's qubit in state 0 prime. Okay, and just to remind you, where 0 prime So I've just used 0 prime, right? The 0 prime eigenstate, and not the 1 prime eigenstate. So where 0 prime is square root 2. So I should equally well in terms of uh, eigenstate 0 prime of sigma x. Okay. So, this we had written already in C equation 3. Okay. All right. And now let's just check. Okay. So check, I mean, is this really right? So check for equation 8 and 7. Okay. So let me start with equation 8. So I have square root 2, 3, and now 0 prime a um, is, well, it's written out here. So 0 prime a, so this is a plus 1a, right? And then, of course, 0b there plus, okay, just that second term. And then, of course, here you can see that this, you see how this gives you back. You see 0a, 0b plus 1a, 0b, and then the final term. So trivial, right? And so this is, of course, so it all checks out, right? Now here's your second remote assignment. Remote assignment 2. Um, you know, similarly as what we just did here, show that equation 9 is the same as equation 7. Okay. Now, you might wonder why I'm assigning you such trivial things to do. Well, because I had promised that I will not give you any math. But when I started preparing these notes, then I find that the only questions I can really ask that are sort of reasonable ones and simple ones are math. And so I'm compensating by giving you some very trivial math questions. Okay. And again, you can solve this in just 1 or 2 lines and take a picture, send it to me, and you will get your extra credit. So these are like 2 in-class assignments, that type of, 2 extra in-class assignments. Okay. Well, so we can show that these are all the same. Okay, so now we can talk about the final slide and where the magic occurs. So here's what we're going to do from this equation 7, 8, 9, we can immediately, without really any controversy, make some very simple deductions. Okay, and what we're going to find is that these deductions that we're making are sort of based on local realism, and Einstein is the one, of course, who sort of, and it really boggles the mind. I mean, tell me, where am I going wrong here? Like, I'm not really, I'm using local realism. It'll become clear what I mean by both of those words, local realism. But let me just go through the arguments. All right. So here's what I'm going to do. Let's ask for the probability. I'll write it out in English. probability that Alice uh, does a sigma z measurement on her qubit pair. So it becomes sort of complicated if I just talk it. So let me just write it. So probability that Alice, okay, uh, does, and actually, yeah, Alice does, and Bob will do the same thing. So does a sigma z measurement on her qubit pair, or on her qubit, and obtains the result -1. Because she could have obtained +1 or -1, right? Sigma z has two eigenvalues, +1, -1. So let's say she does a sigma z measurement on her qubit and obtains the result -1. And Bob also does a sigma z measurement on his qubit and obtains, this is the quantum magic. And you tell me if you disagree with, I mean, I hope you will not think that I've been overselling this, because it is truly mind-boggling, okay? So Bob also does a sigma z measurement on his qubit and obtains the result -1. Let's just look at this, right? So this is equal to, let me, I don't want to keep writing all that English all the time, so I'm going to go probability that Alice does a sigma z measurement on her qubit and she obtains -1. And similarly, comma, Bob does the same thing and obtains a result -1. Okay, so what is this going to be? What is this probability going to be? So um, if Alice, and uh, let me get this table out. All right. So if Alice does a sigma z measurement and finds the eigenvalue -1, you see there's the -1. That means that the state for her qubit is now collapsed to the eigenstate 1, right? So that means that her qubit is now 1a. And that's for Alice, right? What about Bob? Well, Bob also, uh, his qubit, with the same logic, needs to be 1b. Okay. So we're asking for the probability of getting this state 1a and 1b. Alice's qubit in state 1, Bob's qubit in state 1. We're asking for this probability. Okay. Now remember that the state that the initial state that Alice and Bob were sharing is the Hardy state, named after Lucien Hardy. Okay, that's the Hardy state. And we're asking for the probability that we would get this state. Okay, so you can always, so basically you need to ask for the overlap of this state with the initial state, right? And you'll notice that if I look at the initial state there, so I'm going to say, I'm going to say here, look at equation 7, right? And you'll notice that the state 1a, 1b, there is no overlap of that state with any of these three. So when you try to close this with those two states, with the two state formed by those two, then you'll find that there is no overlap. So you can conclude that this probability is going to be 0. Okay. Well, what this means is that this means that um, from this sigma z measurement, uh, both Alice and Bob can never can never obtain the result, can never simultaneously obtain the result -1 simultaneously, right? They can never both, okay? Never obtain the result -1 simultaneously because that probability is zero. And what this means is, and this is all, I mean, there's no flaw in this logic, which means that at least one of the sigma z measurements, by Alice and Bob, at least one of them must yield the result +1 because those are the only must yield the result +1, right? Because if they can both can never get the result -1 simultaneously, then at least one of them has to obtain the result +1. I'm
Unknown
okay.
caller.
Sorry, that's my pharmacy, my medications. All right, so there you go, right? So at least one of them has to obtain the result +1 from their sigma z measurement. We've established that. Okay, now the next thing then is that okay, so if one of them has to get the result +1, then there's only two possibilities. Okay, so there's must yield, at least one of them must yield. And so this means that there are two possibilities. Either um, Alice gets the +1 result or Bob gets the +1 result. So just let's look at both of them. So two possibilities. Uh, Either Alice measures a +1 or Bob measures from his sigma z measurement a +1. Those are the only two possibilities. Okay, so uh, I'm doing this. So let's look at one. The possibility. Let's consider the case that Alice gets it from her sigma z measurement. She gets a +1. Okay, and ask uh, for so now consider the case this is that Alice gets a +1 measurement from her sigma z and ask for the probability that that ask for the probability actually like you can well, let me write it out. Ask for the probability that Bob obtains a value, a result. I'm using the word result, so let me just put that in. Obtains a result +1 from a sigma x measurement. Okay, so just bear this out. I mean, you'll be rewarded at the end. Obtains a result +1 from a sigma x measurement. So I'm constructing this sentence just like this, that probability that Bob obtains a result plus one from a sigma X measurement. Okay. Of course, it's a conditional probability because, this is the case where Alice has already obtained plus one from a sigma Z measurement. So it's a conditional probability. You're asking for the probability that Bob obtains a result plus one from a sigma X measurement, given that Alice got plus one from a sigma Z measurement, right? That's what this is. So what? How do I write this? I write this as probability that Bob does a sigma X measurement, right, and obtains a plus one, given that, okay, not a comma, given that Alice obtained a plus one from a sigma Z measurement. Okay, that's what I'm asking for. Okay, so how do I evaluate this? Well, so it's just like, that probability up there. So let's see. So Alice, when she did her sigma Z measurement and obtained plus one, she put her uh, qubit in which state? Uh, so Alice did a sigma Z measurement and she got an eigenvalue plus one. That means that her qubit collapsed into this, was in this state zero, right? So 0A. And sigma X now for Bob, and he gets a plus one eigenvalue. Well, we looked at the eigenvalues for sigma X. The plus one eigenvalue, you see, you get it for the plus one here, and that's the eigenvalue for zero prime. So his state collapsed into zero prime. Okay. So this probability, so now we're looking for, um, we look for the probability that we can get this state, okay, given the initial state is the Hardy state, right? So let's look at so the Hardy state, there's equation 7, but also 8 and 9 describe the Hardy state also, right? So if I look at, so let me write this just like I did the other one. So the probability for this, so look at equation, and this time we'll look at, so 0 prime b, we'll look at equation 9, all right? Look at equation 9 for Hardy. Okay. And when you look at equation 9 for Hardy and ask for the overlap with 0 prime b and 0a. So I noticed that there is a state like that, 0 prime b, 0a, right? And it's not a simple projection, just like we did the last time. We just said, oh, look at the projection of, project the Hardy state given here onto, the bra, 1A, 1B, right? Not the ket, but the bra. And you can see that, there's no overlap, and so you get zero. Well, this time it's a conditional probability. It's not um, it's just a simple overlap. So what you need to do is, but it's very simple to calculate because you're already given. So I'm looking at equation 9. You're already given that you are in this. Alice has collapsed her state into the zero, her qubit into the state zero, right? Well, so given that you're already in this state, that takes away this guy, and the square root 2 over 3 becomes a 1, right? Because this guy doesn't exist, so it's gone. So you're just left with the 0A. Alice's measurement has already ensured that. And now Bob, therefore, is guaranteed to be in 0 prime. Okay, so this probability is actually going to be 1. All right, cool. And similarly, now let's consider the other case. Okay, this other case. So either Alice had, as a from her sigma z measurement, either she got the +1 or Bob got the +1, right? So now let's look at that other case. Now consider the other case where Bob is the one who did the sigma z measurement and obtained a +1, right? And ask for, just like that, similarly, you ask for this time the probability that um, given that Bob is the guy who measured the +1, what's the probability that Alice now from her sigma x measurement will get? It's the flip of this. So now Bob's the guy who did the sigma z measurement, got a +1. What's the probability that Alice will do a sigma x measurement and obtain a +1? Okay, so let's just evaluate this. And okay, so if Bob does the sigma z measurement and gets a +1, that means, well, just following the same logic like that, that means that Bob's qubit is now in 0 and Alice's qubit is in 0 prime. Okay, and so to see what, and again, it's conditional probability, right? Given that. Okay, and so now to evaluate this, I will look at equation 8 for the initial state, Hardy, right? So let's go do that. Here it is. Okay, and I look at equation 8, and indeed, I see a 0 prime A and a 0 B. And of course, given that Bob has collapsed his state into 0 B, the possibility that his qubit would be in state 1 is gone. And so that this goes away, the 2 square root 2 over 3 goes away. That's the only state that you have to be in, right? And so given that Bob measured his qubit in state 0, then what is the probability that Alice measures her sigma x measurement to be in state 0 prime? Well, the probability is 1, right? So I got 1. Okay, so now we can figure out the really amazing part of this. Okay, so what these two results are telling me is that, from these two results, the conclusion is inescapable that this and this, these are telling me that at least one of the sigma x measurements, sigma x measurements by Alice and Bob, you know, at least one of them must yield the value +1, right? Because there's only two cases that could have existed uh, for the sigma z measurement. And we considered both those cases. And then both those cases individually tell us that at least one of these measurements has to yield the value +1. Okay. Well, this means, and here's the important conclusion from this, that this means that it inescapable logic, it follows that sigma xa and sigma xb cannot both take the value -1, because at least one of them has to be +1, right? We just calculated that. So it follows that sigma xa and sigma xb, meaning that a measurement by Alice of sigma x and a measurement by Bob of sigma x, those measurements cannot both take the value -1. Okay. So from all this, we are saying that if you were to um, measure, and I'm down to my last slide now. Okay. So what this is telling me is that that is that the probability of sigma x by Alice giving -1 and so now comma, not the conditional, sigma x by Bob, measurement by Bob giving -1, this has to be 0. Okay, as predicted by above logic and calculations. This probability has to be 0. Okay, because as we saw, um, you have to have at least one of these will exist. One of these sigma x measurements by Alice or Bob will yield a +1. You'll get one of these two cases has to happen. And if they happen, then you cannot both take the value -1 for the sigma x measurement by Alice and Bob. All right. Okay. But so, but if I were to apply quantum mechanics, see now I can apply the rules that we know from quantum mechanics because this probability is a simple, I want this to happen and that to happen. There's a comma in there. And this I can simply evaluate, okay, because it's like this probability, right? And so you do remember that, you could have, I mean, we reasoned it out, but you could have just said that this probability is nothing but, you know, uh, the state 1A, 1B projected on, or the overlap between this and the state Hardy, right? That's how we've always evaluated probabilities, right? And then absolute value squared. And then we did this. We looked at the Hardy state. We looked at the Hardy state. Where's my Hardy state? Yeah, we looked at the Hardy state and we said that, oh, look, I mean, there is no this state 1A, 1B, the bra like that has no overlap with any of these three. And so that's how we said it's 0, right? Now, a similar calculation cannot be done for the conditional probabilities, like we'd have to be more careful, all right? But now that we've use these conditional probabilities and impeccable logic, really, to come to the conclusion that this should be 0. We can test out this prediction by actually calculating this, using our what we've learned so far. So now we can say, but from quantum mechanics, the probability of Alice obtaining a -1 from her sigma x measurement and Bob obtaining a -1 from his sigma x measurement, well, that's just, well, let's see, this gives you the state, let's see, so if Bob measures a -1, what does that mean? He will on sigma x, so -1, there you go. So that means he's collapsed the eigenstate into the 1 prime, right, for Bob. So he's collapsed it into 1 prime for Bob. And yeah. And Alice also has collapsed her qubit into 1 prime, right? So this is an easy calculation. It is the overlap of 1 prime A, 1 prime B with the initial state, the Hardy state, right? Absolute value squared. right? So, and we can calculate this out easily, all right? So what is one prime? Well, here's here's the state one prime. We wrote this on slide 2, all right? Toward the bottom. So let me write out one prime. So actually, we'll do the absolute value squared at the end, right? Well, okay, now let's just, that's okay. It's such a simple calculation. I could assign this to you, but I just want to show you the result, so I'm just going to do it, okay? So this is absolute value, and then one prime, well, it's given right there. So I have a 1 by root 2, and I have a 0, and this is for Alice. So 0 uh, Alice minus 1 Alice, like that, right? And then multiplied by 1 prime B, right? So that's 1 over root 2, 0 Bob minus 1 Bob. And then I have the Hardy state. And the Hardy state, we shall, and again, because this time, now we've expressed this in terms of the zeros and ones, the eigenstates of sigma z. So let's use use equation 7 for Hardy. Okay, and so that's 1 over root 3. I've written it over there. And I have a 0a, 0b plus 1a, 0b plus 0a, 1b, and absolute value squared. Okay, so use equation 7. Use equation 3. Okay, and now this is easy to do, right? So I have, first of all, I have 1 over square root 2, 1 over square root 2, and then square root 3, like that. And then the way I would do this is, so we have a 0 Alice, 0 Bob, minus 0 for Alice and 1 for Bob, minus 1 for Alice, 0 for Bob, and then plus 1 for Alice, 1 for Bob, like that, right? And multiplying Hardy, which is 0 Alice, 0 Bob, plus 1 Alice, 0 Bob, 0 Alice, 1 Bob squared. Okay. So, okay, so the 2 becomes a 4, so 1 over 12, and then I have the rest stuff. Now, what do I have in here? Well, the 0a, 0b will close with this 0a, 0b. So this and that, right? And so I'll get a 1 from that. Then the 0a, 0b does not overlap with any of the others, right? There's always a 1 with a 0 to make that overlap go to 0. Okay, then I go to the next term, 0a and 1b, and I see a 0a, 1b, right? So this term goes with that term, right? And there's a minus sign there, so 1 minus 1. And so all these, it works out beautifully. And then, the 1a, 0b, and yes, there is a 1a, 0b. So 3, right? And there's a minus sign, so minus one. And then this guy has no overlap, right? So I have this. And so the point is that I got a zero prediction from um, the other way that I was thinking of it. And from just a math quantum mechanical calculation, I get a 1 over 12. It is not equal to zero. So what I'm calling quantum magic and what Hardy revealed in this work that he did is that Hardy's work actually reveals this remarkable conflict between what we call local realism. Okay, so this was by the above logic and calculations uh, uh, born from local realism. Okay, so what's local? We used the very remark, like very sane logic that and correct logic that physical influences cannot propagate between Alice and Bob at speeds greater than c. Okay, and realism means that realism implies that there are properties of, so Alice is the one sending, well, I mean, so there are properties of Alice and Bob's qubits, that exist. Actually, to make this a sentence, properties of Alice's and Bob's qubits exist, uh, whether or not they're measured. Okay, so the if so there's a remarkable conflict. Let me finish this and then I'll tell you where the flaw is. Remarkable conflict between local realism and quantum mechanics. Okay, and so far in all measurements to date, and by the way, the name given to this remarkable conflict, this remarkable conflict is is termed this remarkable conflict is termed non-locality, which we also discussed in the EPR paradox. But I believe that, so I used the mini lecture to drill down deeper and ex expose or reveal this non-locality even better. Okay. And in all measurements done so far, quantum mechanics wins. Okay, no surprise there, but still, I mean, in a sense, it is a surprise. Now, let me tell you what the flaw was in the local realism logic. As it says here, we assume that properties of the qubits exist whether or not they're measured. So, some of our deductions here were made on the basis of we assumed that these measurements were made, but they really weren't. We assumed that these measurements were made to come to a conclusion about another measurement. Now, this measurement we could easily do, like we could actually easily calculate using the laws of quantum mechanics, right? And this measurement, so we can actually predict this measurement by just doing simple quantum mechanics and we get an answer, all right? This same measurement we tried to predict or calculate by using two other measurements that were never done. Okay. And so they gave us a conclusion which is at odds with what the quantum mechanics calculation was. And now both of them are equally compelling. Like, I mean, you really think that, well, which one is correct? Is the quantum mechanics prediction correct, or is the local realism, now that we call it local realism, is that prediction correct? And the only way is to resolve is by doing a measurement, and the measurements have always shown that quantum mechanics wins. By the way, these um, like uh, well, okay, no, I don't want to go there. I was going to talk about Bell measurement, Bell states and stuff, but so there you have it. I mean, this to me is actually magical, like I use everything according to my intuition, like what I did here. This is completely justifiable logic. I don't see any flaw in there. Um, from my classical and from my worldly experience, I would say that this always has to be true. The only reason this is not true is because we started with an entangled state. It's because of the quantum entanglement that you got a completely wrong result from, your classical or worldly logic. Okay. But you have to go back to the quantum mechanical math to find the accurate result. Okay. So, well, all good things must come to an end. That is the end for this lecture and for this course. Just wanted to share that with you. Hopefully, you liked it, and I hope that you stuck through till the end and saw the really amazing result that we got. All right. Um, well, bye. Take care. I will send you an announcement that sort of asks you to reminds you to do those two very simple calculations and send them to me. And the next thing is, of course, that I will post the solutions to the homework that you just handed in uh, as soon as possible. Okay. Well, thank you. And I'm going to stop the recording now.